is Cromer, Josh, and Grace. They did some work dealing with carbon nanotubes. So if we give them a warm welcome.
Hello, my name is Stephen Cromer. I'm Josh Seerdorf.
I'm Grace VanderWoude. Today we're looking at we're observing the effects of radiation on single-walled carbon nanotubes. So the first thing we have to ask ourselves when we're talking about nanotubes and any type of nanotechnology is, what are nanometers? I want you to imagine a meter, right? Like this big. Now cut it into a billion pieces. That's about 1 times 10 to the negative 9th of a meter. Well, it is 1 times 10 to the negative 9th of a meter. We usually divide our field of view into 3-ish different planes. There's the macroscopic world, the microscopic world, and the nanoscopic world. So for like a 6-foot-tall person, it's approximately 2 billion nanometers, just to give you a size comparison. The boundary between macro and micro is 100,000 nanometers. And now I want you to imagine the diameter of your hair, just a single hair, that's 75,000 nanometers. The smallest the eye can see unaided is 10,000 nanometers, and the boundary between microscopic and nanoscopic is 100 nanometers. So, what we're interested is the world of the nanometers and the nanoscopic realm. So, some interesting figures that we have here are the buttons for fluorine, or a buckyball. That's about 1 nanometer in diameter. And what we're looking at specifically with this project are carbon nanotubes, which can have a diameter of about 1.3 nanometers, right here. But that depends on the actual type of nanotube that you have. Alrighty, carbon allotropes. Carbon allotropes are the pure form of carbon that has different crystal structures. So, for example, ones that people are most familiar with are the diamond and graphite. So, diamond and graphite are both made out of pure carbon. However, the crystal structure gives them completely different properties. For example, diamond has an isometric crystal structure, which gives it a low scale of mineral hardness value of 10, which is the hardest substance known to man or human. The graphite has a hexagonal crystal structure, which gives it a low scale of mineral hardness value of about 1 to 2, which is quite different from the actual diamond. What we're more interested in is graphene. So graphite is made out of sheets of graphene. So this right here would be 1 sheet of graphene, if you can imagine it sort of extending out as far as it needed to. But the graphene is stacked on top of each other to make graphite. So they're held together by VanderWoude forces. As I said before, the button for fluorine is another carbon allotrope. It is a fluorine molecule, or called C60 because it is composed of 60 carbon atoms that are covalently bonded together. If you imagine a soccer ball with all of the pentagons and hexagons it has, that's exactly what this is. It's also called a truncated icosahedron, and my example is currently being passed around. So another carbon allotrope that exists is the carbon nanotube. Okay, I don't have a picture. So it's carbon nanotubes are, if you can imagine a sheet of graphene, like we said, rolled into a tube, that would be the structure of a carbon nanotube. However, the graphene isn't actually rolled, it's just, that's how we conceptualize it. And we'll talk about the different properties that the different types of rolling has later. It is covalently bonded together through sp2 hybridized orbitals. So when 2 carbon atoms share electrons, it makes a sp2 hybridized orbital. And so each carbon atom in the carbon nanotube makes 3 bonds per, so it makes 3 bonds per each molecule. What are carbon nanotubes? As I sort of said before, carbon nanotubes are rolled graphene with sp2 hybridized orbitals. The different chiral or rollout vectors give different chemical properties to the nanotube. And as a general structure, the carbon nanotube is capped at the end by half of the fluorine molecule. So half of the Buckminster fluorine is capped by that. Properties. So in terms of steel, carbon nanotubes are 200 times stronger, and they have 5 times the elasticity, which is not to be confused with plasticity. In terms of copper, carbon nanotubes are 5 times more electrically conductive and 15 times more thermally conductive. They're also 1,000 times. They have 1,000 times the electrical capacity or capacitance. And capacitance is defined as the ability of the body to store an electric charge. This is important in materials that are going to be used in space and fabrications of that nature. So let's look at different types of carbon nanotubes. There are the single-walled carbon nanotube is what we should all be most familiar with, since it's the one I described. But as I have said before, it's a layer of graphene rolled into a seamless cylinder and capped by half of a fluorine molecule. Multi-walled carbon nanotubes are composed of concentric single-walled carbon nanotubes of increasing diameter. They are always metallic because of the different wall structures that they have. 2 types of multi-walled carbon nanotubes are Russian doll or the Matryoshka nesting doll because of how they are nested together. And then there's also the parchment multi-walled carbon nanotube, which is graphene just rolled around itself to make walls in that way. The outermost wall, however, differentiates the conductive properties of the multi-walled carbon nanotube. So, and another special class of multi-walled carbon nanotube is the double-walled carbon nanotube. As the name implies, it has 2 walls. The outer wall is used for bonding or as a substrate in chemical reactions, and the inner wall is kept pristine and used for conductivity purposes. So.
All right, so depending on how carbon nanotubes are grown, they can have different geometric structures. These structures can be broken into 3 categories. The first is zigzag, and if you look at the diagram, you can see that the bonds form a zigzag line. The second is armchair, which looks like it has steps, and the third is chiral, which has a spiral structure. The spiral of a carbon nanotube affects the conductivity. On the right, you can see a hexagon grid. This represents what a carbon nanotube would look like if we could unroll it. These 2 blue lines represent where the sheet would connect to itself if we could roll it back into a carbon nanotube. Now, we want to find a point on one of these lines that intersects a carbon atom, which would be the corner of one of the hexagons. That point is called point A. And from point A, we want to draw a line called the armchair line. The armchair line divides the hexagons in half. And now we want to find the closest point on the other blue line that intersects a carbon atom. And that point is called point B. Then we want to draw a vector from point A to point B. This vector is called vector R. The angle between vector R and the armchair line is called the wrapping angle. An armchair carbon nanotube has a wrapping angle of 0 degrees. A zigzag carbon nanotube has an angle of 30 degrees. And a chiral refers to any carbon nanotube that doesn't have an angle of 0 or 30 degrees. To determine conductivity, we have to look at vector R. Vector R is written as NM. If the difference between N and M is a multiple of 3, then the carbon nanotube will be metallic, meaning that it can conduct very well. If the difference between N and M is not a multiple of 3, then the carbon nanotube will be semiconducting, meaning that it can only conduct when voltage is above a certain amount. Now we're going to look at some of the applications for carbon nanotubes. Carbon nanotubes have been mixed into other materials and have been shown to significantly increase the strength and reduce the weight of the material. These composites will be extremely useful for building structures that need to be light yet strong. The composites can also conduct thermal energy and electricity, so they can be used to create devices for dispersing energy. Carbon nanotubes can also be used in electronics. Transistors are what provide a computer with all of its computing power. They are typically made out of silicone, but carbon nanotube transistors are faster and more efficient. They can also be produced more easily because they can be printed. Carbon nanotubes have also been used to create better solar cells. The solar cells use carbon nanotubes and titanium nitride. The carbon nanotubes were used to create an electric network inside the solar cell. The solar cells were more efficient and cheaper to produce. This can be very important because current solar cells are very expensive and not very efficient. The applications that we are most concerned about with our project, or most concerned about for our project, are those that deal with carbon nanotubes in space. NASA is investigating uses for carbon nanotubes in spacecrafts, and carbon nanotubes can make faster, more reliable electronics, as well as composites that are stronger and lighter. However, before they can be sent into space, we need to ensure that they will survive in the space environment. Our experiment is designed to test whether or not radiation will have an effect on the structure of carbon nanotubes. We designed a payload that will carry the single-walled carbon nanotubes that are suspended in deionized water. The payload will travel 100,000 feet into the stratosphere. They will be carried on a weather balloon along with several other payloads. The payload has a mass limit of 1.2 kilograms, and for our experiment, it had to be heated. We also decided to put the vials of carbon nanotubes into an airtight container that you can see on the picture on the left or right here. This would ensure that they are not affected by the pressure changes during the flight. And the balloon will be launched August 1st, so we focus primarily on the design and construction of the boxes.
For our box design, we decided to go with the triangular prism. Both of these boxes are the same dimensions. It is 9 inches long, 2 8-inch sides, and 7-inch base. The PVC pipe running through the center of gravity is 12 inches long and will house the flight string so it can be attached to the balloon and other payloads. For the box construction, the exterior of the box is constructed out of foam core, which is wrapped in mylar, also known as BOPET, biaxially oriented polyethylene terephthalate, or a space blanket. This space blanket will help deflect UV rays to prevent mixed signals of radiation. The entirety of the structure was hot glued together and held together with aluminum tape. The interior of the box is lined with fiberglass insulation, which the insulation was also wrapped in mylar and then hot glued into the interior of the structure. The PVC pipe that runs through the center of gravity is also wrapped in insulation and taped together with aluminum tape. For the box internals, inside of this box, this is our actual flight box. There's this 8-inch PVC pipe, 2 inches in diameter, which will house these vials of our samples. This is just water, though. It'll also contain a hobo data logger, which will measure humidity and temperature. The reason we decided to go with the PVC pipe is it keeps a constant pressure within. For the heating source, you can see that there is an external switch right here, which will power, which control these 9-volt batteries. These 9-volt batteries will run a series circuit through the wires and into the resistors. The transfer of energy creates heat, so that will be our heating source. For the testing of our box, we conducted several different tests. 2 temperature tests, a cold test using liquid nitrogen, which is negative 196 degrees Celsius or negative 321 degrees Fahrenheit. We submerged this test box into a cooler with liquid nitrogen, but we suspended it to prevent the liquid nitrogen getting inside. We did a maximum heat test where we just left our box at room temperature, sealed it up, and put the resistors inside. And I'll explain what the purpose was for later. We conducted several impact tests, a drop test, which is a 40-foot drop from Ross Hall here at UNC, this building right here. It was used to recreate a harsh landing scenario for our payload. We did a stair pitch test where we dropped our test box down flights of stairs to test the structural integrity of the box when if our parachute will drag it across the terrain when it lands. Another test was the whip test. So if you can imagine myself, this box is sealed, spinning this box in a circular motion really fast to simulate speeds near Mach 1 the best we can. I don't think I can spin that box that fast. That's the speed of light. Or speed of sound, sorry, not speed of light, speed of sound. So the circular motion will help us test the tumbling motion when the box is falling. Part of the whip test was a snap test where we threw the box and suddenly jerked it back to simulate when the parachute will open. So these are our cold test results. The starting temperature was 29.52 degrees Celsius. The highest temperature was 38.97 degrees Celsius. The lowest temperature was 15.08 degrees Celsius. While the external temperature was negative 196 degrees Celsius, the temperature in the stratosphere will only reach negative 80 degrees Celsius. So on our graph here, you can see that the y-axis is temperature in degrees Celsius. The x-axis is time in seconds. The blue line is the internal temperature, and the red line is the external temperature. It stopped at negative 101 degrees because that's the maximum, I guess, the temperature gauge device, thermometer, would measure. This test allowed us to conclude that this box can withstand temperatures lower than 80 degrees Celsius. We conducted a maximum heat test where the starting temperature was 25.73 degrees Celsius. The maximum temperature was 56.68 degrees Celsius. The purpose for this test was we wanted to make sure that our resistors would not fail, because in the previous demostat project, their resistor possibly may have failed, and we wanted to make sure that didn't happen. We also wanted to test to make sure that these samples will not boil, because water boils at 100 degrees Celsius, but it's much less the higher you go up in altitude. The y-axis and x-axis are the same temperature here, time seconds here. This is the internal temperature. The duration of this test was approximately 50 minutes. For our methods of measurement, courtesy of Colorado State University, they allowed us to use their transition electron microscope, or TEM. It measures the carbon nanotube wall structure. This here is the thermal field emission gun, or a FEG, where it emits electrons, and here there's an aperture which condenses the electrons and restricts their movement. This is where our carbon nanotube sample was located, and the electrons are focused on the sample. These lenses help focus the image. The image is then processed into this storage device, and this storage device allows us to see the computer on the monitor right there. For the single wall carbon nanotube, this is an image that Dr. Roy Geis imaged for us. He imaged about 40 carbon nanotubes, multi-wall, single wall, and double wall. After the flight, we intend to contact CSU again to measure our experimented carbon nanotubes. We will look for wall degradation. Other methods of measurement are Raman spectroscopy and Raman spectroscopy measures the band gap, and band gap is how easily electrons move from one atom to another. The different bands show the compound structure. Near infrared range measures the photoluminescence from electromagnetic radiation. Certain excitation wavelengths of electrons of carbon nanotubes will cause them to fluoresce. And as you can see this graph, when it gets to a certain wavelength, it will cause them to create a photoluminescence wavelength. Here are our references. These are all of our image references. There were a lot of them. And so our acknowledgements.
Alrighty, so we would like to thank Ryan Salian, undergraduate student, Dr. Matthew Seemack, Dr. Bob Walsh, and the rest of the UNC Physics Department. I would like to thank my research sponsor, Xcel Energy, and we don't have them up there. We'd like to thank the Colorado Space Grants Consortium and NASA, and I would also like to thank my family.
I would like to thank the head of MAST, Dr. Steve Anderson, as well as the director of FSI, Lori Ball. We would also like to thank our RAs, Sophia Semina and Christopher Krause. And I would like to personally thank my scholar sponsor, the Wall Science Foundation, my research sponsor, Union Pacific, and my family.
I'd like to thank CSU and Dr. Roy Geis for allowing us to use the TEM, Sean Hoskins and Nicole Wood, our advisor, Rebecca Kipp. I'd like to personally thank my scholar, the Adolf Koch Foundation, and I would like to thank my research sponsor, Union Pacific, as well as my family. Any questions? Ooh, that was quick. It vibrated.